Thank you very much for the organizers for inviting me. What I am not grateful for is to putting my lecture after this presentation by Professor Lamberto, which was so terribly interesting.
I wanted to apologize that I have to leave because I teach tomorrow, so I'm very, very sorry. I'm so sorry to do this.
Thank you anyway for your presentation.
Well, I will look online. Thanks, bye-bye.
Title of my talk is Zimmer Effect and Babies' Names, and well, the work is done in cooperation with Małgorzata Krawczyk and Antoni Dudejczyk from the same university. And the abstract is given here. In a nutshell, simulations of the Simmel effect are performed for agents in a scale-free social network. The social hierarchy of an agent is determined by the degree of her or his node. Particular features, once selected by a highly connected agent, become common in lower class, but soon fall out of fashion and extinct. Numerical results reflect the dynamics of frequency of American babies' names in 1880-2011. You can wonder where are Cyberemotions here. Okay, there is no Cyberemotions, but still there is some contribution from emotions, because once we have baby and we give him a name, we want his future to be better than ourselves. We want to put the baby CV in higher class than in ourselves, in better situation. And to give a name is some kind of magical, let's say, method. So we have emotions, and this emotions enters to the Simmel effect, which I am going to explain shortly, soon, because the outline of my talk is what is the Simmel effect, why we select scale-free networks, why names, the algorithm of calculation, which is formulated by Roberto Pedone and Rosaria Conte more than 10 years ago, our numerical results, some more information, names, and conclusions. Simmel described in long, elaborate way this effect, which I mean, more than 100 years ago, but the shorter definition or description was given again by Pedone and Conte. So this answer, what is Simmel effect, is like that. Agents are not only inclined to follow, but also to distinguish themselves from others. Zimmer described fashion as a combined effect of these two attitudes. When social groups are ordered by rank, agents imitate symbols designating the higher hierarchical levels and abandon those symbols which designate the lower levels. As a consequence of this dynamic, the status symbol will rapidly spread through the population, proceeding downwards from the higher to the lower level of social hierarchy. However, as soon as these symbols spread, they will be abandoned and replaced with new ones. So the Zimmer effect is this movement of status symbols from elites to lower class. And they extinct and they are replaced by new symbols which again move from up to down, etc. And the structure of social stratification is preserved during all this process. So this is the Zimmer effect. Why scale-free networks? I think I don't need to argue that some social networks are scale-free. We have many papers about that in literature. Many social networks cannot be stated to be scale-free because they are too small. So we need good statistics to to say that a given network is scale-free. But anyway, the more important reason why we use scale-free networks is that degree is a convenient measure of the status. Higher degree, higher status. More connections, higher status. And this is accepted, this statement is accepted for a long time, since the contemporary Bible of social network structure in '94 till recent reprints by Mark Newman. And in this reprint, he shows the rank as a function of degree, and the function is always monotonous and increasing. So let's take it as granted. And this is the slide which exemplifies the order of imitation. I imagine that Gary Cooper is in the middle, and Bronisław Cieślak is the imitator of imitator of imitator, okay? And nobody follows him. But this is my personal view. Why names? Because we have data, and these data are very interesting and beautiful, they provide also troubles. And here we have a trouble because there are 5 classic names: William, Robert, James, John, and Mary. And all of them started, the popularity started to increase abruptly near 1910. And all of them are bimodal functions, and all of them have even some special peculiarities of the structure of the second maximum. So, obviously, they are not independent. Making statistics, we would like to treat these names as independent, but they are not. And these 5 classic names belong to top 10 names. Top names are taken here as having the largest popularity in 1 year during the whole century. So they are very popular. So they produce a bias of statistics. So we cannot omit them in the analysis. So this is a trouble. Obviously, there are some historical or cultural reasons which influence the trajectory, the time dependence of the popularity. The top, first most popular is Linda, which was very popular already in 40s, but near 1947, a song appeared, which was very popular, composed by a soldier coming back from the war for his daughter. This girl later was a wife of Paul McCartney, but this is other story. So this Linda gets 1,000 newborn babies in 100,000 in 1 year, in 47. This is top record, okay? So there are data, and what we see in these data, still, this is not a statistical fluctuation. We always see an increase and later decrease, but this decrease in many cases is more slow. We analyze by eye inspection first 100 names, and we see it relatively often that this lambda shape is characteristic. Of course, these 5 classic have not lambda shape. Still, they decrease slower. Well, why names, why networks? So we should make a glance back what other people did, but this glance is not too far, because here we have one paper by Pedone and Conte, which I already remarked, and what is calculated there is the characteristic of the distribution of frequency of names. Mainly, they use 4 methods. Is it a pointer? No. They use 4 methods to compare. They calculated the variability and variance of the distribution. That's all. There are 3 more papers, all of them from last year. Great, thanks. Yes. Thank you, thank you. There are 3, I must buy something finally. There are 3 more papers. 2 of them analyzed that just the shape of the distribution of frequency of names by Wentian Li and Xi, Chang, and Chang. And what is particularly important is paper preprint of Damien Zanet, who analyzed also this increasing and decreasing shape of the popularity of names, but his analysis is kept within physics because he discussed the effect as activation inhibition process. So the society is a kind of medium. In this sense, our approach seems to be a step in good direction because we consider a psychological or sociological effect introduced not by ourselves but by specialists. And in this paper, the fragmentation was calculated. They call it difference, but they call it inequality. But it is just a measure of how the frequency are not equal. If there is only one name, this is 1. If there are many, many names with equal popularity, this is practically 0. So this is a measure of diversity. This is about algorithm. Don't read this text. This is a script for me, okay, if necessary. This, just let's look at these graphs. This is an example of a local structure. These are nodes, and the connectivity of these nodes plays the role of their social class. The connectivity of this node, number of neighbors, 1, 2, 3, 4, 5. This is a representative of elite. This is middle class because he has only 3 neighbors. This is lower class because he has only 1 neighbor. Okay? So the movement of symbols is from this node perhaps to this node. So what can happen here? There's a process of imitation of somebody from higher class, and there are 2 examples. Either this man, this node, can follow this node and accept his status symbols. I don't mean that 4 is better than 1 or worse than 1. This is just symbols, okay? The inequalities, it could be colors or letters or hats or anything. So this is an imitation process when this node imitates this one. This is imitation process when this node, which was 4, accepts the symbol of this one. But also, this representative of elite can change this status symbol, invent a new version because his neighbor has already 3 and he wants to be different. So these processes are going on in a scale-free network. This is the whole simulation. Okay? Here we have a couple of numerical results. Q is number of options. How many values can a status symbol have? If Q is small, the popularity of given symbol increases till a given value, then does not change. For small q, we have no effect. They are equal and they remain equal. There is no place to be different. But if q is 30 or more, we see cycles. All these curves are moved to the same starting point, where it's like to be different. This is logarithmic scale because if I use another scale, we cannot see anything. The distribution of times is very wide. But we see that the popularity increases, then decreases. We can even see the lambda shape, although it is reverted in a logarithmic scale, but the maxima are about 10,000, and the extinction is about 10 times longer. So this is, we can see lambda shape, it's here. For all larger values of Q, we see the same pattern, but the next result is that the lifetime of the cycle is shorter if Q is larger. This is the time distribution of lifetime, and we see that the shorter value is characteristic for larger number of options. And this is the rule. This is the rule which we see in. So this is important because cycles are shorter if there are many names, okay? Quickly they appear and disappear. This is a comparison of, I would say, characteristic or typical pattern or typical plot, but I know that it is, it's not a good method to say that something is typical. We have many shapes, but anyway, if we look for simplest cases, we see Debra, which is pure lambda shape, and if we take a simplest case from our modeling and adjust the scales, we get almost the same. But there are also historical biases. An example is this young lady, Shirley, which was already popular in 30s, but then Shirley Temple appeared as in movies, and her popularity of this name jumped from 15,000 almost 3 times in 2 years. But later, girl became not adult, but not so young and beautiful. So we see again jump back. Anyway, this is historical bias, and we see more these biases in statistics, and this 5 classic is a good example. This is the scale-free distribution of frequency, but we did not reproduce it so I just show that we see it. Perhaps it's interesting. These are names which are very, very popular, but they are rare. In this year, no, 2 years ago, Jacob is perhaps most popular. On the other side of the scale, there are names which have 6 or 10 representatives in the whole country in a given year, in this year. Okay? There are many years which you could not imagine that they are continuously invented. This is the fragmentation, which is not new because it was found by other people. I show it because it's important for me. You see there is the overall tendency is decreasing, but there is a maximum, local maximum, and we don't know why. We don't analyze that. We have not means to analyze that. But this is a matter for history of culture or something like that. These are data, statistical data on top 20 names, and this is artificially or symbolically divided this set into 2. The criterion, symbolic criterion, was if the popularity in 1935 was more than 2,000 or less. We see here the case where this was larger than 2,000 already in 1935, and all these 5 classic names come into this category. And I show it to demonstrate that they are more wide. But later, this is Linda, and all these peaks are shorter. So the hypothesis is that the larger diversity, the shorter the scale. So we tried to check it in a more quantitative way. We defined something like half bandwidth for a plot, which is of different shape. We find a maximum, then we find the time where this half of this maximum is obtained for the first time and for the last time. And this difference of these times is a kind of bandwidth, half bandwidth. And this is the plot of the half bandwidth versus T1 when this popularity starts. Red crosses are these top 10. We have these 5 classics are here. Green squares are next top 10. The maximum falls into this range from 50 to 60,000 in 1 year. Blue dots is remaining 47 names. All of them, for all of them, the popularity, maximal popularity is larger than 25,000 in 1 year. Okay, and we see that this plot mimics to some extent this diversity. Okay, this fragmentation index. The small fragmentation index, large diversity, small bandwidth, okay? This is what we can say. But, of course, doubts remain because, as I said before, these names should not be interpreted as independent. There is some historical effect which causes, and this is consequence. I have the computer scientist or a physicist cannot comment this origin of this effect. Conclusions. The model of the Zimmer effect proposed by Pedon and Conte is applied to scale-free network, where no degree is assumed to play the role of social status. The model reproduces the following stylized facts on American babies' names. First, popularities of most names increase, then decrease more slowly. Second, the half bandwidth of these maxima are negatively correlated with the name's diversity, larger diversity, smaller bandwidth. I should add that today, in our democratic world, elites are dictated by media and not by aristocratic origin, and this last slide is an illustration of this. Thank you for your attention.
Thank you very much. Thank you for taking the time. Any questions?
I have a question related to the topic, but have you wondered about some correlation between names and connections and the number of social connections? So, are there bots, for example, have more average connections than Lindas or I don't know?
What do you mean by connection?
So, is there any correlation between name and popularity in group or something? For example, Bob have more social connections.
We will drink coffee. You must explain me this.
Okay.
Sorry, I don't understand.
Sorry.
So, thank you very much for that interesting talk. I'm sure we'll all be looking at our babies' names.